let's learn to convert Epsilon Nfa to DFA, thereby proving the equivalence between Epsilon Nfa and DFA. Before getting into the concept in detail, let's have a look at the various finite automata that's available in brief. This is one automata which is shown here. So here if you look at delta from a state Q0 on an input symbol, the destinations is not one and is many, right? You may either stay back in Q0 or you can move to Q1 or you can move to Q2. There are multiple possibilities. From Q0, when you apply input symbol 0, the stay back can either be in Q0 or you can move to Q1 or Q2. So if at all, from a state on applying on input symbol, when there is a possibility to go to multiple states, if at least for one state, we call this to be non-deterministic finite automata. The name non-determinism means you cannot be very sure on where you will reach when you apply a particular input symbol. Coming to the next type of automata, this is one another case where along with your input symbols like A and B, we do have a special symbol called epsilon. In this language, we call epsilon to be the empty string. The length of epsilon is supposed to be 0, which means there is no symbol. So what is the purpose of epsilon? Okay, it is like a null state or a silence in a language. So when you denote an edge labeled epsilon, it means you can reach the destination without consuming any input, right? So without consuming any input, it allows you to reach a particular state. For example, when I am in Q0, okay, so when I apply epsilon, where can I move? There is a possibility to reach either to Q1 or to Q2. That is, what does it mean? From Q0, when I apply epsilon, there are two destinations. Either you can move to Q1 or you can move to Q2. But in fact, this epsilon itself is a empty string. So what does it mean? When you are set to be in Q0, almost you are set to be there in Q1 and Q2 also. So this is one special type of NFA which is particularly for the convenience of the user, right? So when we are we want to represent some idea to the end user community in a more elaborative manner, we can use this epsilon transition. But this NFA or epsilon NFA both will not be of use when you come for real-time implementation, and that's where we end up with a specific deterministic automata where from a particular state when you apply an input symbol, you will have the transition only to one state. Okay, so from Q0 on 0 it is only to Q0. From Q0 on 1 it is to Q1. From Q0 on 2 it is to Q2, right? Similarly, from Q1 there are transitions on 0 and 1, but there is no transition on 2. So a complete DFA is like you have to define, if the transition is not permitted, you can take it back to a dead state, okay, which is almost like an exception. So this is not permitted as part of it. So from Q1, when you reach the next symbol or when you read the next symbol as 2, you can enter into an exception which is a dead state. A similar way is here. In Q2, there are transitions only on 1. So on either case, which is 0 or 1, you can enter into a dead state. So this is what we call as deterministic finite automata. So given these three automatas, okay, the languages will be one and the same. Okay, so the class of languages that NFA accepts and epsilon NFA accepts and DFA accepts will be same, and hence each should be converted to one another. So an NFA should be converted to DFA, which already we have seen in one video through a procedure called subset construction, and this epsilon NFA should be converted to DFA either directly through this way by using the same subset construction, or you can go through this also, like epsilon NFA can first be converted to an NFA, then it can be converted to a DFA. Come, let's see how to convert epsilon NFA into a DFA. So it actually goes in two phases. In the first phase, you have to compute epsilon closure of every state. So it's very simple that when you compute epsilon closure of a state, it means the set of all states that you can reach only through epsilon transition. right? It will first include that state, because when I say I am in Q0, I will be in Q0. Then whichever states I can reach without consuming input symbol, those are the states I set to be in. That's what is epsilon closure, and hence it can never be empty. Okay, it can never be empty, so that needs to be taken into account. And once this epsilon closure is constructed, as usual, you apply the subset construction procedure with a minor modification that at each and every destination, you have to again compute the epsilon closure and then you have to proceed. So that's what is the two-phase in the construction of epsilon Nfa to DFA. So first you need to compute epsilon closure, then you need to construct subsets of epsilon Nfa. That will be the part of your DFA. So let's try to convert this epsilon Nfa into a DFA. As usual, the first phase is to construct epsilon closure of every state. So, how to compute epsilon closure of Q0? So, I'll start with Q0. So, what to do? You have to first include Q0, and then you have to include states that are reachable from Q0 on epsilon transition alone. So, from Q0, just see where and all you can move on epsilon edges. So you can move to Q1, you can move to Q2. So add these two. And your task doesn't end there. When you can reach Q1 from Q0 on epsilon, you have to again check from Q1, is there any possibility to reach any other state on epsilon transition alone. Here there is only one outgoing edge which is on A, and hence no. And from Q2 also there is only one outgoing edge, and hence you can stop here. Then epsilon closure of Q1. So first I will include Q1, then find any state that is coming out of Q1 with epsilon transition. There is no such state, and hence it is this. Then comes epsilon closure of Q2. Okay, so this is the state. There is no outgoing edge on epsilon, and hence you have to just add Q2. Then epsilon closure of Q3. Yeah, I'll include Q3 first. Then look at the transitions. You have two outgoing edges on epsilon, one to Q5, another one is to Q1. So Q5, Q1. Now from these two destinations, again you need to check whether there are any epsilon outgoing edges. From Q1, no. And from Qi, yes, it is to Q6. Yes. Now epsilon closure of Q4. So add Q4 first, then find out the transitions. There is only one epsilon outgoing edge which is to Q2. That's all. Then epsilon closure of Q5. So include Q5 first. There is only one outgoing edge, that too on epsilon, which is to Q6. And finally Q6, it is to Q6. There is no outgoing edge. So once this is constructed, the next task is to compute DFA states. Like the NFA to DFA construction, the procedure is pretty simple. You have to start with epsilon closure of Q0. Okay, in NFA to DFA conversion, we start with Q0. Always here you have to start with epsilon closure of that state. Okay, the input symbols remain same, it is A and B. So what is epsilon closure of Q0? Already we found this. It is Q0, Q1 and Q2. Okay, so you have to find the transition from Q0, Q1, Q2 on A. So from Q0 we don't have transition on A. From Q1 it is to Q3. Okay, and then from Q2 on B it is to Q4. So as usual, you have to bring this state to be the next state with epsilon closure included. Epsilon closure of Q3. Okay, so bring this destination over here with epsilon closure. So what is epsilon closure of Q3? It is Q3, Q1, Q5 and Q6. Okay, this becomes the next state. So apply A from here. So from Q1 it is to Q3. Okay, and from Q3 we don't have transition. From Q5 no, from Q6 no. That's all. On B, if you take So from Q2 there is a transition. From any of the state we don't have transition on B. From Q3 no, Q1 no, Q5 and Q6. So this becomes an empty state. Now bring this state down. So epsilon closure of Q4. Right. So it becomes Q4 comma Q2. So that is the next state from Q4 to Q2 on A. From Q4 on A it is to Q5. From Q2 on A there is no transition. And on B, if you see from Q2 on B you have a transition which is to Q4. That's all. It is over. Then from Q3 again you need to define. Since it is already defined, you can use the same state. From Q5 we have it defined. So epsilon closure of Q5. So what is epsilon closure of Q5? It is Q5 comma Q6. So Q5 comma A no transition, Q6 comma A no transition. It is a pi set. Then from Q5 on B no transition, from Q6 on B no transition. That's all. Right. From Q4 if you take again it is to same state. That's all. No new state transitions are found. So you can name the states like A, B, C and then D. Okay. Now what is this? A on A, it is to Q3. So what is Q3? It is state number B. A on B, small b, it is to Q4. Q4 is capital C. That's all. B on A, it is to Q3. This Q3 is again capital B. Okay, it is to self loop. It is to same state. Then on Q4 it is to Q5 which is capital D, and on Q4 it is small b, it is to Q4, it is to C. Okay, so that's all. Your DFA is done. Now how to redraw this DFA? You will have 4 states A, B, C and then D. As usual A will become the start state, right? How to identify the final state? Wherever you have the final state of this, which is Q4. Q4 is there in B, so this becomes a final state, and it is there here, it becomes a final state. So B will be a final state and D will be a final state. Now add on the transitions. A on B, it is to A on B, it is to C. So A on small b, it is to C. Right. Now from B, there is a self loop on A and there is no transition on B, so you can introduce a new state called dead state on B, right? Then coming to state C, on A it is to D and on B it is to self loop. We'll make it as D1 in order to differentiate. Okay, have a look at here. It accepts A star or B star A. Okay, here A star. Okay, so one time you have to read A to reach Q6 and then you can repeat any number of times, and when you have multiple B's you must have A, okay, in order to come to a conclusion. So that is how Epsilon Nfa should be converted to DFA. Thank you.